revision of partial fraction methods. The next method of integration that I want to cover involves us considering integration by partial fractions. For this reason, it's worthwhile that we first revisit the methods required to manipulate and solve partial fractions. There's a further benefit in the fact that partial fractions will be required for the study of Laplace transforms in our electrical principles classes. So we will need then to be able to solve a partial fraction situation, or at least split a fraction into two partial fractions for electrical principles. So, first of all, the opposite direction. What do we need to do to turn those two separated fractions into one fraction, i.e. do the algebraic addition of those two fractions? Cross multiply what? If you're going to write that as one fraction, what have you got to do? Yeah, and how do you do that, Curtis? You do, yeah. So what would make it easier about that then? That won't serve the purpose of what I'm trying to teach here, that's for sure. So yes, the common denominator is those two multiplied together. What we got to do at the top? Exactly, you've got to multiply the 3 by x minus 2. We've multiplied it by what we multiplied the denominator by to get that. Yeah, and this will be this side x plus 1, and in the middle there a plus. Yeah. So if we multiply all that out, what do we end up with in total? Multiply those brackets. So we've got x plus 1 plus 3x minus 6. And multiplying out the bottom, we get minus 2x we've done minus 2 times x, yeah, plus x minus 2. And then we can pull together like terms, so x and 3x is 4x, 1 minus 6 minus 5. So the top line, 4x minus 5 over x squared minus x minus 2. Yeah? Okay, so that at the top is the partial fraction version of what's down the bottom. So today's session is about how we go from functions like that and turning them into partial fractions so that we can integrate partial fractions. which is summarised on the next page. The reverse process of going from 4x minus 5 over x squared minus x minus 2 to 1 over x minus 2 plus 3 over x plus 1 is called resolving into partial fractions. Two conditions. First of all, we must be able to factorise the denominator. Write it as two factors. There. The second thing is, unless we want to do some further manipulation to make it as such, the numerator must be at least 1 degree less than the denominator. So in our example, we got 4x, that has a highest power of x of 1, and the denominator has a degree of 2 because the highest power of x is 2. Okay, so they're the conditions, and you'll only be given examples that fit those conditions at this stage. Okay. There are two types of function that we're going to look into that we require resolving into partial fractions. Those involving linear factors, where we go from a function like that of linear factors into partial fraction of up to three separate fractions, and those involving what's called repeated linear factors, where we've got one factor in there to the power of 3 or more, and we'll be doing that method as well. Okay, so we'll be taking a look at both of those situations and examples in those situations today. So, first example. How do we go about resolving 11 minus 3x over x squared plus 2x minus 3 into partial fractions? Yeah, factorise the denominator. How do we do that then? We've got x squared plus 2x minus 3. What's the process of turning that into two separate factors? We know we're going to have two pairs of brackets. And we know in this case we've got x in each of them, because then multiplied out we'd end up with x squared. Yep, exactly. So the way I tend to do it is write out the options that I've got for two numbers that multiply together to get minus 3. So what options will give us minus 3? 1 and minus 3, minus 1 and 3. Which two of those, the next question is, which two of those add together to give us plus 2? It's got to be them two, isn't it? So it must be in here minus 1 and plus 3. So that's the denominator factorised. What we can do then is we can say that 11 minus 3x over x squared plus 2x minus 3 is equivalent to 11 minus 3x over x minus 1 x plus 3. Yeah. And then we can say that that's also equivalent to two partial fractions like so, with the denominators being written as two unknowns, A and B. Yeah. And normally, when you write this out, you'd leave that bit out and just go straight from saying that is equivalent to that. Yeah. And write either of those. In fact, don't necessarily need to write all three. So if you're already given it in that form, you just say that's equivalent to the two partial fractions with these two factors separated. Yeah, they're added. Sorry. Right, yeah, good spot. They're added together. Well, A and B are constants to be determined. So, can anybody remember what the next step is? What do we need to do with these fractions over here? What did we do with that other example? What did we say we had to do with the earlier example? Yeah, we need to get a common denominator. Yeah. So we've got to say 11 minus 3x over x minus 1 is I times x plus 3 over that common denominator plus b, and we've got to multiply that by this side, x minus 1 over all right. Everybody was happy with that so far? And so now that bit there yep, we can now write that as that, because we got the same common denominator now to both halves. Yeah? Anyone remember what the next step solving the partial fractions is? So how do we, the question is really, how do we find the constants A and B? Correct. Let the top equal 0. Anyone else? There is letting something equal 0, but there's a term for what you're going to do. If these two are equal, then surely, if the two denominators are equal, and they're exactly the same, then surely 11 minus 3 must be also equal to all of that bit. Yeah? That must be true, mustn't it? Yeah. So what we say we do is equate the numerators. We say the two numerators are the two of that left-hand side and the right-hand side are equal to each other. I.e., 11 minus 3x is equal to I x plus 3 plus b x minus 1. Now what can we do? How can we, what you're looking for is to make either that equal to 0 or that equal to 0. Yeah? Yeah, so if you start, let's start with x equal to 1. Yeah? If x is equal to 1, then all of that bit is equal to 0. Yeah, so we've eliminated b. Okay? And then we can say 11 minus 3 is equal to I 1 plus 3, writing it all out. So we've substituted the value x is equal to 1 in. So we can say 8 is equal to 4a. A must be 2. Everyone happy with that? And then we also let x equals minus 3 that means 11 minus 3 times minus 3 is equal to b times minus 3 minus 1. That bit's minus 4b. 11 minus 3 times minus 3. 20. Therefore, b is equal to minus 5. Yeah? 20 over minus 4 is minus 5. Alright, so we got values for I is equal to 2, b is equal to minus 5. We then go back and put them into that. I'll write it out again, I think. A is 2, B is minus 5. Therefore, (11 minus 3x over x squared plus 2x minus 3 is equal to 2 over x minus 1 minus 5 over x plus 3. That's that resolved into that pair of partial fractions. Okay, everyone happy with that? Yeah? So, second example, I want you to start having a go at is convert that fraction into the sum of 3 partial fractions. Benefit of the video. So with this problem, we've done is split the initial function up into 3 partial fractions, then common denominator, so we multiplied the a, b and c so that we're equivalent and there's a common denominator. Equated the numerators, and initially let x is equal to minus 1. That eliminates this b term here and the c term here, and we can substitute x is equal to minus 1 in and determine the value of a. Then let x is equal to 2, which eliminates that term and that term, and therefore we can use that to find b, which is equal to minus 3. And lastly, if we let x equal minus 3, it'll eliminate the a term and the b term, allowing us to find c, which is equal to 1. We then can put the 3 values for a, b and c back into the separated partial fractions, and the job is done. Okay, everybody okay with that? Within reason? Yep. Right then, moving on. Resolving function with repeated linear factors into partial fractions. So we've got 2x plus 3 over x minus 2 all squared. We're going to resolve that into partial fractions. Now what we can do is say that's equivalent to I over x minus 2 plus b over x minus 2 squared. Okay? And then we want to make the common denominator of that is common denominator of that is what we started with, isn't it? Yeah. So we've got to say that's equal to something over x minus 2 squared. So what have we had to multiply this side by to make that denominator equal x minus 2 squared? The b denominator. Yeah, so it's just b that side, because we hadn't multiplied that by anything. What do we have to multiply that by to make that denominator x minus 2 squared? So over this side we've got a x minus 2 and a plus in the middle. And that bit there, 2x plus 3 over x minus 2 all squared, is equivalent to that. Go on. Yep. The x in the original function you were given, you're told that the 1 denominator is x minus 2 squared. Yep. The standard form of that in partial fraction form is x over a over x minus 2 plus b over x minus 2 squared. Yep. That's the formula for it. If you had cubed there, you'd also have plus c over x minus 2 cubed. I'm going to do one like that, or you're going to do one like that in a little while. Okay? That's just the method. Right? That's a repeating linear factor, i.e. that's bracketed and then multiplied by itself. Okay? I don't propose to go through how you derive that from the other method. You don't want to know that, do you? No, nor do I. I'm prepared to take Mr. Bird's word for it that that's the method. Alright? Yeah? So, what we can do now then is do what? What did we call it? Equate numerators, didn't we? So we can say 2x plus 3 is equal to I x minus 2 plus b. If the bottom end is equal, if the denominator is equal, the numerators must equate as well. Now what are we going to do? Let x equal 2, therefore 2 times 2 plus 3 is equal to, if x is 2, that bit is nothing, plus b. Therefore, b equals 7. All follow that. Now what can we do? Yeah. What value are you going to make it then? Y? We're going to let x equal. What's the best thing to let it equal? Yeah. Who said that? You, Ed? Did you say let x equal 0? Yeah. Which means 3 on that side is equal to a minus 2a, in fact. 0 minus 2 is minus 2, plus b, which is 7. So minus 4 is equal to minus 2a. A is equal to 2. All follow that? Yep. Hence, in summary, 2x plus 3 over x minus 2 all squared is equivalent to 2 over x minus 2 plus 7 over x minus 2 all squared. The reason for this is next week we look at how we integrate, for example, a function like that. We can't do it directly, but we can integrate these. Yep. So in your notes on the next page, there is repeating linear fractions example, the cubic term. So I'm going to start you off. You can say that 3x squared plus 16x plus 15 over x plus 3 cubed is equivalent to I over x plus 3 plus a over x plus 3 squared plus c over x plus 3 cubed. Yeah. Then we equate numerators. So we go 3x squared plus 16x plus 15 is equivalent to I x plus 3 squared plus b x plus 3 plus c. Then, if we let x equal to minus 3, it'll eliminate the a and b terms. Yeah? all of that is equal to c, because x equal to minus 3 eliminates those two, and we end up with c equal to minus 6. The problem now is we've got a value for c, but the only value we can give to x that will eliminate a is minus 3, but that would also eliminate b as well. So you've got a problem. What you have to do here is multiply out the brackets, or these two terms here and here, well, or that one in that right hand side. So you have to do this. 3x squared plus 16x plus 15 is equal to a times, what's x plus 3 squared multiplied out? 6x plus 9 plus b times x plus 3 plus c. Do we write that out as the c at this stage? So we expand the bracket, the squared term, in the right hand side. Then we can say that's equal to ax squared plus 6ax plus 9a plus bx plus 3b plus c. So we're going to expand that out still further. Okay, so what we've got now is a single squared term on both sides of that equation. If there's 3x squareds on that side, there must be only 3x squareds on the other side too. So we can equate the coefficients of x squared. I.e., we can say 3x squared is equal to ax squared, therefore a is equal to 3. Alright, or not? And then, following on from that, we've got 16 times x on that side, and we've got 6 times ax there, and b times x there. Yeah? So we can equate the coefficients of x. We've got 16x is equal to 6a x plus bx. Yeah. Everyone happy yet or not? We know what a is, so we got 16x is equal to 6 times 3 is 18 x plus bx. Minus 2 x is equal to bx. B is equal to minus 2. And here I've said equate the coefficients, but I've actually written the x terms in. We don't actually need to do that. We could write here 16 is equal to 6a plus b, because it's the coefficients that equate. Yep. I've just tried to do that to show you where it comes from. Alright? So finally, what we can say is 3x squared plus 16x plus 15 over x plus 3 all cubed is equivalent to 3 x plus 3 cubed. That's the final version of splitting that initial function into 3 partial fractions. No, Michael, it doesn't. Elsie doesn't know how to do that. Okay. Bless her, yeah. Well, you know,